Kia ora everyone. I hope you're doing okay. Welcome to the first live stream of term 4. This is going to be a big old review of all of the stuff that you need to know for the selected chemical reactions internal that you're hopefully working on at present. I've heard there might be some issues in terms of loading those videos. I'm going to figure out how to make sure those are working by the end of today, and I'll update you on the classroom if we need to. Okay. What you can see in this image here is a little bit of copper wire, and we dunked it in some silver nitrate. Now, silver nitrate is a lovely blue solution, but when you dunk it, you start to see some interesting things happening. The first thing you see is that the copper starts to get this coating of kind of the silvery compound. It's a solid, and it sits on the surface, and it kind of falls off if you disturb it too much. Over time, you also get a color change in the liquid. Now, what's happening here is a displacement reaction, which hopefully you remember from having gone through the stuff that we've been talking about already. If you don't know, that's okay. That's what this review is for. So in this case, you've got some copper, which is solid, and some silver nitrate, which is aqueous. Now that turns into copper nitrate because the copper in this case is more reactive than the silver, and so takes its place. And the silver, because it can't stay in solution as an ion, it falls out as a solid. And so it accumulates, and you get these kind of silvery deposits on your copper and on the base of the beaker. That also creates a slight color change because copper nitrate is a slightly different color than silver nitrate. So hopefully that will kind of make sense. As we go through this topic today, team, if you've got any questions, you're welcome to fire them off into the chat. But our te rautaki te rā is to talk about the background of this internal. We're going to go through each of our 4 reactions, which are the 4 types you're going to be needing to identify, and then we're going to review the achievement standard and exactly what you need to do to pass. The last thing to note is that the hand-in for this assignment is 6 p.m. on Friday. You must complete it by this stage. If that is going to be an issue, please get in touch with me ASAP. You can send me an email. Okay? Alrighty. Let's look at this internal. So the chemical reactions internal involves looking and classifying these different kinds of chemical reactions based on our own observations. Essentially, we show you something and you write about it. There are only 4 kinds of reactions you will need to know, and we will go through them in this report. This is a 4-credit internal, so it's big bucks here and worth taking some time to nail. The skills that you're going to be working on and that you'll be assessed on are predicting what will occur, observing what occurs, identifying the reaction, writing those word equations, then symbolic equations, then balanced equations, and linking those observations to what you've observed and the types of reaction that you believe it to be, in particular linking to whatever the products are. We also expect that you'll be using correct chemistry vocabulary, which will be refreshing as we go through this. Okay? Here's a nice little image of a reaction. Yeah, due 6 p.m. on Friday. All right. So here's an example of a reaction that we might do. We could drop a little piece of magnesium into some hydrochloric acid, and then we'd see some bubbles being formed, and the magnesium slowly turning into something else. Now, what you could look there in terms of doing your observations is that the magnesium is a silvery coloured solid strip. The hydrochloric acid is clear and colourless. It is also a liquid. That the bubbles appear to be colourless. You might also, in this case, we might tell you that when you get those bubbles, we test them using the hydrogen pop test and confirm that it is indeed hydrogen. You might find out that the test tube is warm because this reaction is exothermic. It gives off heat. The magnesium gets smaller over time, and eventually those bubbles sort of die down because the reaction is over. We've used all of the available magnesium to do this reaction. So our equations in this case We took magnesium and hydrochloric acid. That's a metal plus an acid. Bada bing, bada boom, that makes a metallic salt. And that hydrogen flutters away as hydrogen gas. We could write that as an equation, which as a symbolic equation, where we just replace all the words with symbols, right? Magnesium is Mg, hydrochloric acid is HCl. Don't get the Cl confused for Ci. Carbon and iodine quite different, right? It's a C and a little L, right? That then forms MgCl2, right? And the reason we know it has to be Cl2 is because magnesium as an ion has a charge of 2+, and chlorine as an ion has a charge of 1-. So therefore we need 2 chlorines to balance our 1 magnesium. We then have hydrogen left over. Now hydrogen, when it turns into a gas, is always H2, right? So that forms H2, and that bubbles away. The third and final step of this, in terms of equations, is balancing. So we need to make sure that we've balanced within the molecules, particularly magnesium chloride in this case. We then need to look, have we got the same number of atoms on both sides? If we don't, we might need multiple of certain molecules for this reaction to be balanced. In this case, for every 1 atom of magnesium, we need 2 molecules of hydrochloric acid. You can also write in what state these various things are in. In this case, the magnesium was a solid. The hydrochloric acid, really, it's aqueous, AQ. Liquid, it might be passable. I'd encourage you to write aqueous instead there, though. The magnesium chloride, if it remains in solution, is a solid. If it disperses into the solution, it's aqueous. And in this case, the hydrogen's a gas. That's the big one, right? So the last part of each of these is going to be around evaluating it. So you're kind of, in real human words, linking what you've seen to the equations you've got. So there's some examples of that there, which you're welcome to have a look at. We've kind of gone through this over the last few weeks. We've had this kind of template where you name the reactants, name the products, write what you saw, write the word equation, put it in the balance symbol equation, and then we've even had like a little box below where you can explain the links together or identify the reaction. So there's examples throughout our sets of slides that we've already put, which you can use to review. That's okay. If you're arriving late, no problems. Whoever you are, boop, boop, just tell me your name and I'll make sure that I mark you as present. Okay, so we're going to look at our first 2 kinds of reactions first. Decomposition and combination. 2 of our 4, we're going to get them through really quickly, right? Combination reaction. Oh my goodness, what could that be? It's a combination. 2 things joined together, right? In reality, you can have a variety of different combination reactions. They get more complicated than this. At this level, we're only going to show you 2 things forming 1 thing, right? Generally, it's going to be like 2 elements joining together. The classic representation of this is A plus B equals AB, right? We've got a whole bunch of examples there for you to have a look at, right? If it's 2 things forming 1 thing, and that's the only thing that happens, it's a combination reaction, okay? An example of this is metal oxides. So you have some magnesium, you have some oxygen, you burn the magnesium, lovely bright thing that you shouldn't look at directly with your eyes, but it produces magnesium oxide, right? Lovely combination reaction there. And that kind of explains that process here. So that's our first one, done. 1 of 4, all completed. Our next one is decomposition. Decomposition, to decompose, to break down. 2 things, or 1 thing, splits off into 2, right? In reality, decomposition is going to be more complex than this. You can have 1 thing splitting off into 3 or 4, but at this level, it's going to be 1 thing splits into 2, right? So AB becomes A and B. An example of this would be hydrogen peroxide. Well, elephant's toothpaste. You remember that experiment, right? You get some hydrogen peroxide, which is H2O2. You put in a catalyst, and that speeds up it separating into water and oxygen gas. Now that oxygen gas sort of piles up, which is why if you put some dish soap in, and make that reaction happen really rapidly, you get essentially all these oxygen bubbles bubbling up really quickly, and that can make this thing shoot up into the air, which is quite cool, right? We can use a variety of different things to break something down, to decompose something into its components. So heat, catalysts, electrolysis just means kind of zapping it with electricity. Catalysts are kind of the classic. So our decomposition reaction, here's another example. Magnesium carbonate can be broken down into magnesium oxide and carbon dioxide. Yeah, you just might expose it to something that allows for that process to occur. But that's our second reaction, right? We've got another example here. This one was done with heat. You heat copper carbonate, it turns into copper oxide and carbon dioxide. Easy, right? One thing separating into two. That's half our reactions done. And, that was only a couple of minutes in terms of explaining those different reactions there. All good. Okay, we've got a couple more examples of these, but you get it by now, right? One thing splits up into two, that's decomposition. Two things become one, combination. All right. Displacement reactions. This is number 3, right? So for displacement reactions, we've got essentially something coming in and kicking out something else. In this case, we basically only talk about this with regards to cations. So it'll be one cation replacing another cation. Now, our cations have an order that they appear in, right? We have like our top dog cations and our weaklings, right? If a weakling cation is hanging out with an anion and something more reactive comes in, it will kick it out and take its place. It will displace it. So the classic example of this reaction is kind of shown at the bottom here. A plus BC turns into B plus AC, right? The A, if it's more reactive, takes place of the B. The series that we use, which we will provide you with, you don't have to worry about this, we will provide you with this, is the reactivity series, right? Most reactive at the top, least reactive at the bottom. If you have a reaction that is a displacement reaction, it'll only occur if the newbie is more reactive than the one that's already in the compound, right? Hydrogen, or let's use copper for example, copper is not going to displace magnesium from a compound because copper is lower down than magnesium is. On the other hand, sodium will displace iron. If you've got an iron compound and sodium gets dropped in, sodium's going to replace it, right? Because sodium is more reactive. It's going to displace that cation. It's going to kick it out, right? Carbon and hydrogen aren't metals, but they still follow these rules. So that's kind of the general gist of things. So we've got a couple of examples, right? Copper nitrate with silver. Copper and silver nitrate. We did this at the start, right? Copper, if we look at this, where's our copper? Here. And where's our silver? Slightly below. Silver is less reactive than copper. Copper is more reactive than silver. Copper will take the place of silver. It'll displace silver, kick it out of there, and take its place with the nitrate. When this occurs, the silver has nowhere to go, and silver can't really stay as an ion in water, so it falls out as a solid. What we would observe in this case is that you would get this kind of coating of silvery metal on the outside of our copper that would grow and grow and grow and grow and grow, and also you get this color change because copper nitrate is kind of a deeper blue than silver nitrate. So that is an example of a displacement reaction. We have some other examples here. You can pause the video. You might have done this already, but I'll reveal the answers in 3, 2, 1. The key thing here was that last one, zinc and magnesium sulfate. Magnesium is right up the top here. Zinc is here. When you add zinc to magnesium sulfate, magnesium is more reactive. Zinc is not going to displace it. It is not as reactive. All the other ones, the compound is less reactive, or the cation in the compound is less reactive than the metal being introduced. So as a result, they are going to displace it, but just keep in mind that that might come up, right? We might have ourselves an example where a reaction does not occur, and that is because of this reactivity series. Yep, that's all you need to know for that. Now that we've done that, our last type of reaction is precipitation, right? Precipitation refers to precipitates, which is where you have a solid being formed that falls out of solution. In this case, you've got two ionic solutions, so usually two aqueous substances, two substances dissolved in water, because basically that's the only solvent we really deal with at this level. There are other solvents out there, other things you can dissolve things in. Water's the only one we're going to talk about though. You get these two, mix them together, and there's some sort of swapping of your cations, so they swap around. And then it turns out one of them is a precipitate, one of them is a solid that falls out of solution. If you see a solid being formed between two aqueous solutions, you know it's a precipitate reaction because a precipitate has been formed. Hopefully we remember the terms soluble, solute, solution, precipitate. These are all terms we need to be using when we're describing these. How do you tell what the precipitate is? Which of our two things, our two compounds that are formed, is the precipitate? Well, you use the other thing we'll provide you, the solubility rules, right? Solubility rules describe what things are soluble in water and what things aren't. It's a set of rules, we will give them to you, right? You have some lists of things that are all soluble and some rules that have exceptions. Essentially, you need to look at your two compounds that were made and check, are either of these insoluble? If they're not soluble, they're going to fall out of solution. If they're going to fall out of solution, that's your solid, right? And that's also the evidence you use to show your understanding. So in the case of this one, right, we have a silver nitrate solution, which is clear and colorless, and we have a potassium chromate solution, which is yellow and translucent. You mix the two together. The solution remains pretty yellow, but you find a red precipitate forms and falls out of solution. Now, because you know this is a precipitate reaction, we're going to have this kind of swapping over. You're going to have our silver joining with the chromate. You're going to have our potassium joining with our nitrate. So one of those two is going to be insoluble and one of them is going to be soluble in our case. So let's look at potassium nitrate first. Nitrates, every single one of them is soluble. So they're all going to be dissolved in water. Well, let's look at our other one, silver chromate. Chromate. Well, there's nothing in this here, right, which suggests to us that, and by the way, we would give it to you. We would give you the information in there. If we were going to use a chromate. Chromate's a weird one. We would tell you, right? But because you know that all nitrates are soluble, you can have a pretty good guess that you'll be your silver chromate. That's the red thing that you're seeing at the bottom of this reaction. And you notice, oh my goodness, an insoluble solid of silver chromate. Now, for the ones we will give you, we will tell you. It will be in this table. It's not like you're going to have to guess. Okay? So yeah, when you're explaining these, use the rules. You talk about which is the solid. All the ions that hang out and do nothing, they're just sitting there in the water, right? They're what we call spectators. So please call them that. Call them the spectator ions. They're the ones that kind of watch while interesting things are happening. They don't react themselves. This is an important concept that comes up in senior chemistry as well, which is why we introduce it here. So if an ion is hanging out in solution, observing a reaction but not participating, it's a spectator ion. Cool. So yeah, you need to predict the products that are made and explain which one you think is the solid and why. Right? Why is that one a precipitate? Use the rules to figure that out. Just a refresher on the terms. Solutes are the substance you dissolve. A solvent, in this case it's always going to be water, is the thing that is doing the dissolving. Right? Water is a polar molecule, gets in between those bonds, holds things apart. A solution is a mixture of solute and solvent. Right? Cool. Other terms you might need to use are the term dissolve. When you put some solute into a solvent, it dissolves. Use that term. Don't just say you kind of throw it in there or something. Use the chemical terms. Soluble. If something can be dissolved in a solvent, then it's soluble. If it's not able to do that, it's insoluble. Precipitates are the solids that fall out of solution. Happens when you have two ions that essentially are more attracted to each other than the water is able to go in there and stop them. So they form these solids and fall out of solution. Spectator ions we just talked about. Those are those lovely observers that do not participate in the reaction. They are aqueous, meaning that they sit in the water watching. So here's another little example for you to have a little bit of a look at, taken from one of our last week's slides. Here we have some salty water, right? Sodium chloride, colorless solution, reacting with lead nitrate, also a clear and colorless solution. When you mix these two clear colorless solutions, oh my goodness, what do you see? You see this interesting kind of snowy white precipitate. What could that be? Well, firstly, we've made a precipitate from two solutions. So we know that it's a precipitate reaction. We know there's going to be some swivelly swapping going on, right? We swap around our cations. So we have sodium nitrate and lead chloride. So let's look at the two. Let's look at sodium nitrate first. What does it say about nitrates? All nitrates are soluble. So your sodium nitrate, that's not your precipitate, is it? What about lead chloride? Let's have a look. Chlorides, all are soluble except silver and lead. Aha, we found it. So we state something along the lines of, we know that the white precipitate that was formed is lead chloride because the rule that we've been told is that all chlorides are soluble except for lead chloride. State that, you've made the clear link, love your uncle. All done. Okay? So yeah. Here's another example from one we did before. Using the rules, you can also think about it like this in a table, right? You don't have to if you don't want to. But the nice thing here is that they've identified that the sodium and the sulfate are spectators. They're hanging out and watching. Yeah. Whereas the copper and the hydroxide form a solid, and that is a precipitate that falls out of solution. So it's kind of a nice one here because it means that you do actually talk about that other thing. You're talking about the precipitate. So that basically brings us to the end of our full reactions. This is an example of like a full-on question, which kind of steps you through. I'll leave that for you to look at if you want to, right? But the key thing here is you need to link your observations to the parts of the reaction, which I know you're all capable of doing. More details here on precipitation. I just wanted to really hammer it home, but I think you all are capable of understanding that. So, in summary, 4 reactions. Decomposition reaction, 1 thing forms 2. Combination reaction, 2 things form 1. Displacement reaction is when one cation kicks out another one because it's more reactive. And lastly, the precipitate, when you have 2 solutions combined together and one solid falls out. The solid is called a precipitate. That's all you need to know. Things to think about when you're answering this. You need to identify, name and describe products and reactants. So we're thinking things like, is it a gas, liquid, solid, or aqueous for each of these, right? So, for example, we're talking about magnesium and hydrochloric acid. Magnesium is a solid. Describe it that way. What color is it? Well, magnesium's got this kind of silvery color to it. If it's a solution or if it's a liquid, is it translucent or is it cloudy, right? Translucent means like lets light through, right? The reason why you say that is because often when you form a precipitate, the precipitate can be quite small, so that makes the solution look cloudy. So that's kind of why you would describe it like that, okay? The next thing is you're going to have to write some equations. So you might want to get some practice in before you attempt this. Word equations are the easiest. You're just saying, here are the reactants, draw an arrow, here are the products. you can turn those into symbols for your symbolic equation. You can then balance it. You must need to know how to balance equations. To do that, remember, you make sure that the atoms are balanced within each molecule with regards to their ionic charges. You then need to make sure the number of atoms on the left and the number of atoms on the right is the same. If you need any help with this, let me know. Happy to step you through it. The last thing is you need to link your observations to the type of reaction and to the products that you make, right? So just step it through using all the stuff that we've just gone through. Lastly, ensure you use correct chemistry terms. We've been using a whole bunch of them here, but we're looking for words like translucent, soluble, precipitate, all the nice long chemistry words. We want you to show off your knowledge, okay? Lastly, little reminder, this internal is due at this Friday at 6 p.m. If that's going to be a challenge for you, let me know via email soon. We can figure things out, okay? I'll leave up our essentially criteria. The only thing that you might not have covered, or that we haven't really covered here, is that to get excellence, you want to do a little paragraph, and will be spaced for you on the report, to do a compare and contrast. And essentially, you'll be comparing and contrasting two of the reactions that you've done or that you've observed, and talking about like what was different between those two reactions. And usually, I think you have to pick one of them as a precipitation reaction. So you kind of compare the two together, and it's really easy for you to kind of say, well, this is what we observed, and therefore this is this reaction compared to this other one. So here's what's the same, what's different, that sort of thing. Hopefully, that's everything you need to know, and you're feeling more confident about attempting this internal. We will have a Google Meet on Friday in case you want to ask any final questions before you submit your report. Okay? Have a lovely rest of your week. If there's anything you need from me, please don't hesitate to get in touch. Look after yourselves and your mental health. And next week, we will continue our revision around the externals. There's also that video that we put online over the break, which you're more than welcome to use as the first stage of your review. All right. Lovely seeing you all, team. I look forward to seeing you on Friday. Okay. Mate wa.